The granite blocks weighed 8 tons each. 2 portal arches, 5 miles of tunnel, built for a mountain that engineers feared would collapse. On November 7, 1909, Canadian Pacific Railway engineer J.E. Schwitzer stood at the east portal entrance of the lower spiral tunnel in Yoho National Park, watching workers position the final granite arch block. The company had given him an impossible engineering problem: reduce the gradient on the Big Hill section of the Transcontinental Railway from 4.5% to 2.2% without adding 50 miles of track. His solution required drilling 2 spiral tunnels inside Cathedral Mountain and Mount Ogden. The problem wasn't the tunneling. The problem was what happened if the mountain collapsed during or after construction. Schwitzer had studied the 1903 Frank Slide in Alberta. 82 million tons of limestone had slid off Turtle Mountain in 90 seconds, burying part of the town of Frank and killing between 70 and 90 people. The Canadian Rockies were geologically young mountains, still settling, still prone to rockfall and structural failure. Cathedral Mountain and Mount Ogden weren't limestone, but the tunneling would disturb the rock structure. The mountain might shift. The portals needed to survive catastrophic overburden if the interior collapsed. He specified portal arches built from individual granite blocks weighing 8 tons each, quarried from the Kicking Horse River Valley. Engineers in Montreal questioned the specification. Standard railway tunnel portals used 2 to 3 ton blocks. 8 tons was excessive. The rock inside the mountains was stable gneiss and schist. But portal failure was unlikely. Schweitzer's response was documented in CPR engineering reports. The portals weren't designed for likely failure. They were designed for catastrophic failure that would destroy standard construction. The lower spiral tunnel portal construction began June 1908. Workers quarried granite from outcrops 2 miles downstream. Each block required 5 days of cutting and shaping. The granite was harder than the limestone used in other CPR structures. Steel hand drills wore out after cutting 6 inches. Workers used black powder charges to split large formations, and then shaped individual blocks with pneumatic hammers. The blocks weren't uniform. Dimensions varied from 4 to 8 feet length, 3 to 5 feet width, thickness determined by arch position. Keystone blocks at arch peaks were largest, weighing up to 10 tons. The arch geometry was precise. Each block was cut to exact curvature specified in Schweitzer's drawings. Tolerance was 1/4 inch maximum deviation from template. Portal construction method was deliberate. Workers excavated to bedrock, 12 feet below the planned track grade. The foundation was solid gneiss, the same rock forming the mountain interior. Foundation blocks were set directly on bedrock with no intermediate footing. Each block was positioned, then locked with adjacent blocks, using iron dowels 2 inches diameter, extending 18 inches into each block. The dowels weren't structural. They prevented block displacement during arch construction. The arch rose in concentric rings from foundation to keystone. Each ring required precise positioning. Workers used wooden falsework to support blocks during construction. The falsework held each stone until the complete arch ring was placed and the keystone locked everything in compression. Once the keystone was set, the falsework was removed. The arch supported itself through gravitational compression, not mortar strength. Mortar was minimal. Workers placed thin lime mortar between blocks, 1/4 inch thickness maximum. The mortar wasn't load-bearing. It filled irregularities and prevented water infiltration. The arch strength came from block mass and compression geometry. A properly built stone arch becomes stronger under load because increased weight increases compression between blocks. The lower spiral tunnel portal arch consumed 6 months of work. Workers placed 47 individual granite blocks. Total arch weight, approximately 340 tons of granite in compression. The arch span was 22 feet wide, sufficient for single-track railway with clearance for steam locomotive smoke deflection. The upper spiral tunnel portal construction began simultaneously 300 feet higher on Cathedral Mountain. The geometry was identical, except the granite came from the same quarry. The construction crew was different. CPR employed 2 teams to accelerate the schedule. Both portals were completed November 1909. The tunnels themselves consumed 2 years of drilling. Workers used compressed air drills and dynamite. The lower spiral tunnel curved 234 degrees through Cathedral Mountain, descending 45 feet while traveling 3,255 feet. The upper spiral tunnel curved 226 degrees through Mount Ogden, descending 48 feet while traveling 2,922 feet. Combined, as the spirals reduced the gradient from 4.5% to 2.2%. The gradient reduction solved the operational problem. Before the spirals, westbound trains required 4 locomotives to climb the big hill. Runaway trains were common. Between 1884 and 1909, there were at least 3 fatal runaway accidents on the Big Hill section. Eastbound trains faced a different problem. The 4.5% descent was too steep for safe braking. Engineers used special track brakes, but trains occasionally lost control. The spiral tunnels eliminated these problems. The 2.2% gradient allowed normal locomotive operation. 2 locomotives could pull standard freight trains. Braking was manageable. The safety improvement was immediate. After the spirals opened in 1909, runaway accidents on this section stopped. But Schwitzer's portal design wasn't tested by operational loads. It was tested by the mountain itself. Winter freeze-thaw cycles began immediately. The portals faced temperature swings from -40°C in January to +30°C in July. The granite blocks expanded and contracted. While the thermal coefficient of granite is small, but accumulated over 340 tons of stone, the expansion forces were significant. The arch geometry absorbed these stresses. Compression increased during winter as blocks contracted and locked tighter. Compression decreased during summer as blocks expanded. The arch remained stable through both cycles. The quarter-inch mortar joints allowed enough movement to prevent block cracking. Rockfall tested the portals in 1911. A section of Cathedral Mountain face above the lower portal released during spring thaw. Approximately 1,200 tons of rock and debris fell 400 feet, hitting the portal arch on the west side. 3 granite blocks were impacted directly. The arch held. Block displacement was measured at 3/8 inch. The blocks were repointed with fresh mortar. The arch remained structurally sound. The catastrophic load Schwitzer feared never materialized. The mountains didn't collapse. The tunnel interiors remained stable. The gneiss and schist rock inside Cathedral Mountain and Mount Ogden proved stronger than anticipated. And modern geological surveys show no significant structural movement in either mountain since tunneling. The 8-ton granite portal blocks were overbuilt for a failure that didn't occur. But the portals endured. Canadian Pacific Railway converted from steam to diesel locomotives in the 1950s. The granite arches supported the new motive power without modification. Diesel locomotives were heavier than steam. The additional weight increased portal loading. The arches showed no stress. Track maintenance in 1975 required portal inspection. Engineers measured arch deflection, block displacement, and mortar condition. Deflection was unmeasurable within survey equipment precision. Block displacement showed maximum 1-inch settlement over 66 years, concentrated in foundation blocks, within design tolerance. Mortar condition varied. Exposed faces required repointing. Protected faces showed minimal degradation. Modern engineering analysis in 1995 calculated portal safety factors. Based on measured loads and granite compressive strength, if the portals were overbuilt by a factor of 3.5, they were 3.5 times stronger than required for the actual loads they carried. Schwitzer had designed them for mountain collapse. They instead carried trains. The portals still function today. Canadian Pacific Railway operates freight trains through the spiral tunnels daily. Modern freight cars are heavier than 1909 equipment. The portals support increased loads without concern. The 8-ton granite blocks, placed 115 years ago, remain in their original positions. No blocks have been replaced. But mortar repointing occurs every 25 to 30 years. The granite itself requires no maintenance. A structural engineer reviewing Schwitzer's specifications in 2015 called them remarkable. 8-ton blocks for portals that would carry railway loads, not building loads. Foundation to bedrock where soil foundation would suffice. Arch geometry calculated for overburden 3 times any credible failure scenario. The assessment concluded these portals were not built to carry trains. They were built to survive mountains falling on them. The portals still stand. The granite blocks placed in 1909 still carry structural loads through compression. 0 rebuilds, 0 reinforcement. The mortar has been replaced in sections. The stone has not. The mountain collapse never happened. The catastrophic overburden load never materialized. The 8-ton blocks designed to survive disaster instead survived time.